Hi, my name is Moshe. I'm the founder and CTO of ScaleDB, and I'll be talking about ScaleDB, what we do, and how we integrate into the MariaDB, the platform that MariaDB provides. My presentation would have three parts. The first part will show you a quick demo of what we do, so that you would have a sense that of the functionality and the features and the value that ScaleDB provides. Ashwin here that works at ScaleDB will help me at that part. Then I'll talk about the market, what value we provide to the market trends, and the value that we could bring to customers and application in the space. The third part of the presentation, I will be talking, I'll give a high-level explanation of the infrastructure that we provide, the product, how it works, and how people could leverage the functionality to solve data management problems that they are interested to deal with. So with this overview, we'll start. Just one thing before we start the demo, one thing that I want to highlight is our position in the data management space. We could think about we could think about data in two ways. We could think about data volumes, the increase, the growth of data volume, which is something that all of us consider and deal with when we manage our data. And we could think also about data velocity, which means the pace in which data is accumulated into our database. Usually people, when they have data, they would go and manage it in the database. So we know that MariaDB is a great solution to manage data. Obviously there are other solutions. However, when data grows, people take the data out from the database and try to find solutions elsewhere. And the reason is that when data volumes are very, very large, it's very hard to manage those amounts of data in the database. There is another trend where people go to in-memory solutions. And people go to in-memory solutions when they need a very fast response. If we work in a database and we write the data on disk, the disk has some penalty in terms of performance. So to get fast performance, people would use in-memory databases. But we all know that we cannot use very large data sets in memory. It's very expensive to put petabytes of data in memory, and we'll talk about it when we look at the market trends. ScaleDB offers a solution that fits very well into this model, such that we could manage huge amounts of data that are being updated inside the database, inside MariaDB. We could scale MariaDB to manage billions of rows and do very fast inserts of data to the database. So with this overview, we'll go and see the demo. And my third part of the presentation would try to explain how ScaleDB works and how we are being able to manage those amounts of data very efficiently. So Ashwin, can you? So before we started the talk, when we were sitting there, we started to load data into the database. So you see here, what you see here is data that is being inserted to a cluster of MariaDB instances that we manage at our office, not far from here. So in this cluster, there are 4 MariaDB instances. All those instances update shared data. Now you could see the instances by their names. So we have a machine called the Gilroy, a machine called Pacifica, Los Altos, and Belmont. So those are 4 machines. On every machine, we've got 10 threads doing inserts to this shared data. On this column here shows us the pace in which each thread makes the updates. So we could see here about 20 to 25,000 inserts per second for every thread. So with 4 machines and 10 threads doing an insert on every one of those machines, we are pushing data here in a pace which is next to 1 million inserts per second. So what you're seeing here is a live insert where 1 million inserts per second are being pushed into the database. The second thing that we would do query of this data. So while those inserts are running, Ashwin will run some queries. And we have, as I mentioned before, we have multiple MariaDB instances. So we are, Ashwin is getting connected to one of those instances, and we will run those queries from one of those MariaDB instances. As I said before, and we'll talk about it in the third part of the presentation, all the data is shared by all the instances. So every instance can see all the data all the time. So we have a table here, and which is a very simple table. It's a transaction table where different stores, there are payments done for different things in a chain of stores. So we have things like customer ID, we have account ID, store ID, coupon amount that's being related to this to each transaction. What's important to notice is that the primary key is an auto increment, and there are some special keywords that we use to leverage some of the ScaleDB functionality. I won't go into detail here about those special keywords, but it's very straightforward to define.
Sorry, 1 second. I don't think people in the back can see. Someone's gonna.
I think.
Is that better?
All right. So there are some special keywords that we use, but it's a straightforward definition of the table. There is a primary key here. There is an index by the account number. There is an index. There is an index over time. The reason that we index the time is that there are lots of queries that would be looking to figure out trends as a function of the time. What were the sales between August 1st and September 10, and that's a very important component that I'll be talking about it later. All right, so the first lookup that we would do a lookup by the primary key, but maybe before, you could see that since we started like 10 minutes ago, we're next to 1 billion rows that were inserted to this table. So the first lookup would be by the primary key, and the reason that we do this lookup is for 2 reasons. First, to show that the keys are updated while they insert. It's not just we dump the data somewhere. The indexes that were defined of this table are updated. The second reason is that we'll take this account number, which is a foreign key, and we'll do a lookup by this foreign key. And again, the reason to do it is just to show you those indexes are updated dynamically as the data being inserted. And there are, I think, probably hundreds of thousands rows for this account, so we limit it by 100. But you can see very quickly all the indexes are updated. So with those 2 examples, we'll go to the third example, which I think is more interesting. And the third example would like to get us data within some time frame. So we ask to see all the rows that satisfy a particular condition between some time frame that Ashwin will specify. No, run. Before running the query, we'll reset the statistics. So we'll be able to show you after the run of the query how many rows were evaluated and how much time it took. So we are running a query that asks for all the data within some time frame where the amount is greater than 95 and store is number 5 and coupon is, say, 15. And there are 642 rows that satisfy the query. Can you show how many rows are in the database at this point of time? And it took about less than 5 seconds. Can you show us? All right, so you went to the statistics. So, all right, so we'll look at the statistics first. So what we see that we brought up 642 rows that satisfy this particular query. There are 50 million rows. What's interesting here is that there are 50 million rows in this time span that we consider. So we had to evaluate, because we indexed by time, there were 50 million rows that needed to be evaluated. Evaluating those 50 million rows took about 5 seconds, so that's about 10 million rows a second being evaluated. And obviously we didn't scan the entire file. So the file is, if we do select count, we've got more than 1 billion rows by now. So scanning 1 billion rows would take a lot of time. And the point that ScaleDB offers here is that you could push a lot of data into your database and run very efficient queries if those are the type of queries that you're interested in. And we'll talk about the technology behind it, how it works, and additional features and value that ScaleDB provides. Right.
For those who didn't see, the query was what happened during the last 60 seconds.
Go ahead, please.
What kind of machines these are, the 4 machines what you have, what is configuration?
Yeah, great. That's a great question. So it's not very.
Please repeat the question.
So the question was what type of machines we use. So the first thing to know, this is a disk-based solution. So it's not that the data is pushed into memory. Those are not the high-end machines. Those are commodity machines. Those are 8-core machines. And I think there are 16 or 24 gigabyte on Igor, did you remember, or actually, do you know how much?
Yeah, they're 4-core 8 CPU machines each. The database nodes themselves have about 6 to 8 gigabytes of memory each. The storage nodes have, I think, 16 gigabytes each. So they're very simple machines for the most part.
So nothing fancy here, and customers of ours who are testing it put better hardware. We had just 2 days ago, a customer tested very similar benchmark, got almost 1.5 million inserts per second with slightly better machines. All right. So trying to summarize what we wanted to show is that we push about 1 million inserts per second to the database, and we could do even more than that. If you want, if that's what you need, the solutions are very expensive. Usually people would go to memory databases, which are very, very expensive. So SAP HANA, if some of you are familiar with the solution, claims for 1.5 million inserts per second, but only the memory that they use to be able, it's a memory database, and only the memory that they use to provide this performance is around $2 million. We all know that data volumes are exploding. There is a big growth in the usage of data. Many applications generate a lot of data. There are many devices that generate a lot of data. And there is a need to manage these amounts of data. However, as we said before, it is not simple. And when you get to very large data sets, the solution is to take it, pull it out from the database, and go to places like Hadoop, where you're able to manage data more efficiently, but you pay in that you left the database. It's not transactional, it's not in real time or next to real time. The main problem with managing the data in Hadoop is the gap between the event and being able to query the event. So if you're running something that tries to figure out trends and try to impact some behavior of some application, this lapse of time between the event and being able to query the event could be a big factor. If you're trying to detect fraud, that's obviously a big factor. If you're in a gaming industry and you want to analyze your data and be able to impact the game, this gap between the occurrence of the event and being able to query the data could have a big impact on the value of your data. So we see that people are starting to talk and be interested not only by managing big amounts of data, but also being able to query this data in real time or next to real time. And that's exactly the place where ScaleDB fits. That's the value that we could bring you. We provide a very cost-effective solution where you could manage huge amounts of data in next to real time. We could see the interest around those types of solutions by the different stream processors and different solutions around it. So there is, I don't know how many of you are familiar with Twitter Storm or Amazon's Kinesis and so on. But those are solutions that try to deal with high velocity data, but they're only able to do it by picking at the data as it flows by. Once the data moved, then the data is gone. And in order to put it into the database and be making the data available for querying, as we mentioned before, those are very complex and very expensive systems that needs to be available. So if you need the data in real time, it's very hard to do it. And that's where ScaleDB fits, and that's where we could provide a lot of value. Just to quote a vice president in Amazon saying, MapReduce technologies are good at handling large volumes of data, but they are fundamentally batch-based, and so they struggle with enabling real-time decisions. This is one of a very favorite slide that I have that Mike made, which explains how the difference between the different approaches. We could see that with a stream processor, it's analogous to a case where you look from the side window and you see the view as it passes by. But if you want to revisit something that you looked at before, it's gone. It's not available for you anymore. So the second option is to take the data and bring it to Hadoop, but then you could look only at historic data, the things that are happening right now and are of interest for you are lost. And the last option is the place where we fit, and that is to put it into the database, and ScaleDB with MariaDB could offer this opportunity where you stream your data into the database and be able to query it in real time. The next point is very interesting. Not many people are aware that the cost of memory is so high. One of the things that people say is that, well, memory becomes cheaper. But if you look at the price of memory, if you have 100 terabytes to manage, then just the price of memory is $2 million. If you have 10 terabytes, it's 200,000. So those are enormous prices, and it doesn't make it something which is doable in many cases. According to IDC and Gartner, data volumes have been measured to increase 10 times in every 5 years. And if you think about the cost of memory versus the growth of data volume, you would see first that data volume increase in a much larger pace than the cost of memory. If you look at it at the last few years, I mean, it's getting more and more expensive to manage the data that companies have with memory-based solutions. So again, if we go back to this chart, what we could say is that if you were to use, for example, BigQuery, which is Google's solution, where you could dump your data and run queries against it, and you were doing about 1 million inserts per second, what we've showed you here, the cost would be $86,000 a day. With our solution, it would, since everything is disk-based, the data stays on disk, the cost would be about $46 a day. So, with this market and segment overview, I'll talk a little bit about what we do, how ScaleDB works, and how we can deliver this functionality. So the standard way to work with the database is to manage everything in a single machine, whether it's a virtual machine or a physical machine, where you take the database processing, the ability of the database to analyze data, and you couple it together with a mechanism that manages the data, usually in the disk drives, and does the reads and the writes. And this approach has limitation. It's limited because a particular machine is limited. It has so many CPUs, it has that much amount of memory, it has that much amount of disk, and there is so much that you could do when everything is coupled together. The first thing that we've done is we took the two components, the compute or the database processing component, and we disconnected it from the management of the data. So on the compute component or the database component, you've got the MariaDB instance, and you've got ScaleDB that is treated here like a storage engine. So all the calls that would usually go to MyISAM or InnoDB are being managed by ScaleDB here. But one of the major differences is that instead of having the management of the data on the same virtual or physical machine, instead of those two things being coupled together, we've separated it. So we've got one instance here that does the database part, the compute part, and then another instance that does the data management part. So we call it the database instance and the storage instance. The storage instance manages the data, the I/O piece of the solution, and the database instance manages the database logic piece. The next phase is to say, okay, since we were able to separate those two components, we take those components and we could put them on a network. So on the network, we could have multiple storage instances, and we can have multiple database instances. And one of the major qualities of this approach is that we could scale. We could scale by simply adding instances to the cluster. So with a single machine, you're bounded in terms of how much CPU, how much memory, how much resources the particular machine has. With this approach, you could have as many database instances that you want. So you scale by practically adding CPUs and memory on the database tier. And the same logic works for the storage tier. So if the bottleneck is on the storage, if you have lots and lots of data, you could have multiple storage instances on the same network. Now, every database instance, if we look at this database instance, is able to access all the data on all the storage instances. At the same time, this database instance is able to update or query all the data on each one of those storage instances. So in this architecture, a question that somebody could ask, what do you do if you have conflicts? When you run in a single instance, we know all that we've got a log manager that synchronizes between the threads and resolves conflicts between the different processes that run in a single database instance. In this architecture, we've got a component which is called the cluster manager, and the cluster manager, the job of the cluster manager is to resolve conflicts between different database instances on the same cluster. And there is lots of effort and a lot of logic that we've put in order to make the cluster manager efficient, such that you would be able to do inserts at such an enormous space and at the same time run queries that scan huge amounts of data.
How do you slice the data? Hash or partition or?
That's a good question. It's random. So it's we could think about the storage tier very much like a RAID device. In a RAID, you write the data in blocks and you randomly spread it across all the disk drives that you have in the RAID device. Logically, it's the same thing. We take data, we put it in blocks, but instead of disk drives, think about machines in your cluster or machines in your cloud. So it's completely random.
How do you handle unique keys?
Right. So how do we handle it? So the question was, how do we handle unique keys? So there are two things to understand with this architecture. The first one, the solution is generic solution. It's very much like Oracle's RAC or Exadata, who's familiar with it, and we've got indexes that provide this functionality. For this particular tuning that we've done with the streaming data, the primary key is unique, and the indexes that we showed being updated by account number and by time are not unique indexes. So if you want to add additional unique indexes, it would slow the process. But again, you still get the cluster. So we've got one of a company that works with us did the comparison between us and InnoDB with a benchmark called YCSB, which is a Yahoo standard benchmark. And we showed the cluster, which was similar to the cluster that I demonstrated here, did on the YCSB about 10 times better than InnoDB. And there we used unique indexes. It depends. So to answer your question, we've got indexes that are unique, we've got indexes which are non-unique. Those are hash indexes that we used here. So, and the index and the functionality that you're trying to achieve has some impact on the performance that you would be able to get. But we could support all of those, and it depends on what index you choose.
My question was just that really support unique indexes, and it works.
Yes, absolutely.
So is there something in MySQL that for MariaDB that doesn't work, that works for InnoDB? So do you support all functionality?
Support what?
Do you support all functionality that you can do with the
Orphan?
Do you support all functionality that you can do?
Yeah, it's compatible to InnoDB. So that's a good point. All the functionality, we worked with many customers, and many customers test us, and it's completely transparent to the applications. You take MySQL MySQL application, and you could deploy it on the cluster, and it's completely transparent. And I encourage you to try it. In terms of high availability, the way that we support high availability is by mirroring the data at the storage tier. So every storage node or every storage instance that we showed before is mirrored. And when we write a piece of data, we write it to both the main storage node and to its mirror. So you don't have to worry about slaves or replication. If a storage node breaks, Then you've got the mirror that comes up or always available and support your process. You don't have to do something about it. It's completely transparent. If the cluster manager fails, we've got a standby cluster manager that kicks in and manages the cluster. And if a database node fails, then again, you don't have to worry since all the nodes see all the data. So if this one breaks, just route your queries and your updates to any one of those surviving nodes.
And you can add these storage instances, hot add and add more instances of those.
Yeah.
Does it redistribute the data across the...
So the question, can we add storage nodes? And the answer is yes. Can we do it dynamically? The answer is yes. Then the question was, do we distribute the data again when we add storage node? And the answer is no. So what the approach says, let's say you've got 4 storage nodes and you ran out of capacity or you're IO bound, you want to add more storage node, you add another 2 or 4 nodes, and then these new nodes will get preference with new data that you insert until the entire cluster at the storage tier would be even. And then we'll continue to update all the cluster in an equal manner.
So the distribution is completely random. If I have a table with like 100 rows, it could get distributed across all these 5 storage nodes.
Right, and we want it to be this way because when you've got your queries and your IOs, we want it to be distributed across all the cluster exactly like you want it to be in an array device. In an array device, you strike the data randomly, so you get even distribution of the IOs on the different disk drives. Same concept here, but again, instead of disk drive, think about machines, either on your premise or on the cloud.
And the application just connects to one instance of the database.
Yes, from the application point of view, it's completely transparent. The application sees MySQL. It doesn't know about the cluster. It just works transparently against the MySQL, but the entire data set is available. So to manage, if we go back to the example or the streaming data case, so people to manage those amounts of data take it out from the database and go to NoSQL solutions, and obviously those are not transactional. Joins are very complicated. I'm sure you're aware of all the limitations that you have if you take your data outside from the database and put it in some NoSQL type of solution. And the opportunity that we present is to keep the data in the database, and at least for those types of applications that fit to the streaming data model that I showed, we could go up to 1 million and more inserts per second and run extremely efficiently with queries. So the way that we deal with the queries, or I'll try to share with you just a little bit of the technology underneath the solution is, let's say that we want to look at the query that we showed before, where we want to look at some time interval and ask for all the sales within this time interval where price is greater than 95 and coupon code is such and such. So we connect to one of the MariaDB instances in the cluster, and it doesn't matter which one. And we send the query, this particular query, we send to this MariaDB instance. Then we use the push-down mechanism. We take the query to the storage engine and on the node. And this type of query, we split it, we send it to all the storage nodes that manage the data. Once we do that, every storage node operates on the data in parallel. So if we have 10 storage nodes, we send it to the 10th storage node, and each one of those would process about 1/10 of the data, and they'll all do it in parallel. Once they finish the process, they take the result set and ship it back to the MariaDB instance, and MariaDB will present it back to the user. So these types of operations, if some of you are familiar with Exadata, which is the high end of Oracle, in terms of the functionality, this is very similar to the functionality there. In terms of the question about the indexes and primary keys that Monty had, so for the time predicates, we have a special index that runs on each one of these storage nodes. And that makes it very efficient to run queries by time. And we could reach to evaluating 100 million rows per second and satisfy MySQL very efficiently with result sets over huge amounts of data. So we could show high performance. We showed high performance in inserts. It's very similar to MapReduce logically. It's done in parallel on all the storage nodes. So the last thing that I want to share with you is an example of a success story that we have. So there is a company called Statrix that is using our solution, and what they're trying to do, they try to provide prices of different things that people are interested either to buy or sell. So if you want to sell your iPhone and you don't know how much to ask for it on eBay or Craigslist, you can go to Statrix and they'll give you the price where according to the time or when you're interested to do it. So their problem was that there is a huge amount of data that they need to manage, and this is a startup. They don't have the infrastructure, and they cannot they cannot address those amounts of data in a very efficient way unless they use ScaleDB, and we provided a solution there where they crawl over the internet, and they have crawlers that send them every transaction that is done on eBay, on Craigslist, huge amounts of data. They manage it here. I think they get to hundreds of millions of inserts per day, and it works with a very small infrastructure, a small cluster. They can manage amounts of data that if you were to go to Craigslist or eBay, you would see that those places pay huge amounts of data in order to get performance and functionality, which is similar to what Statrix is being able to do. The last thing they have on their website, we just noticed that they have on their website pictures of their people that work in the company. They are so happy with the solution that we gave them that they added us as they added ScaleDB as a team member there. I encourage you to look at what we're doing, and if this is something which is interesting for you, we'll be happy to talk to you and work with you and do a proof of concept.